We often speak about space and time as if they are familiar things. Space is where events happen. Time is when they happen. We measure them, divide them, and rely on them constantly. Yet when physicists look closely, these two ideas blur together into something deeper and harder to grasp. Even after more than a century of modern physics, we still do not fully understand what spacetime truly is. Welcome to AstraFlow. Here, science drifts like starlight, and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. If you'd like, you can share in the comments where you're listening from tonight, and if these calm explorations help you rest, gentle support through a like or subscription helps AstraFlow continue. Now, let's begin and explore the science of why we still do not understand spacetime. At first, this question may seem surprising. After all, spacetime is not a fringe idea. It is central to modern physics. Satellites rely on it, astronomers use it, engineers account for it, and yet understanding something mathematically is not the same as understanding it intuitively or fundamentally. Spacetime works, but it still feels strange. Part of the difficulty is that spacetime is not something we can step outside of and observe directly. We are inside it at all times. Every thought, every movement, every pause unfolds within spacetime itself. Unlike objects we can hold or processes we can isolate, spacetime is the stage on which all experiments take place. That makes it unusually hard to study. Another challenge comes from scale. Our daily experience happens at slow speeds, moderate gravity, and familiar distances. Spacetime behaves gently there, but when speeds approach the speed of light or gravity becomes intense, spacetime behaves very differently. Time stretches, distances shrink, paths curve. These effects are real, measurable, and confirmed, yet they do not match how our intuition expects the world to behave. There is also the issue of language. Words like now, here, and simultaneous feel clear in everyday life. In spacetime physics, they lose precision. Events that seem simultaneous to one observer may not be simultaneous to another. The idea of a universal present moment begins to dissolve. Our language struggles to keep up. Perhaps the deepest reason we still do not understand spacetime is that our best theories disagree about its nature. General relativity describes spacetime as smooth and continuous, like a flexible fabric. Quantum physics, on the other hand, describes reality as restless and discrete, filled with fluctuations. When we try to combine these pictures, they resist fitting together. The mathematics becomes unstable. The concepts begin to fracture. Despite this, physics continues calmly forward. Predictions remain accurate. Technologies function. Observations align with theory. The mystery is not a failure, but a sign of depth. Spacetime appears to be both well-behaved and profoundly subtle, familiar and deeply unfamiliar at the same time. As we move through this exploration, we will not rush toward conclusions. Instead, we will move slowly, examining what spacetime is, where our understanding works, and where it quietly fades. There is no urgency here. Only a steady unfolding of ideas, one step at a time, allowing the question itself to remain open and gently present. When physicists use the word spacetime, they are not simply combining two familiar ideas into a convenient label. They are pointing to a shift in how reality itself is described. Space and time are no longer treated as separate backgrounds where events occur. Instead, they form a single connected structure that shapes how events unfold. In everyday life, space feels like a three-dimensional container. You can move left or right, forward or backward, up or down. Time feels different. It flows in one direction, from past to future, at a steady pace. These experiences are so consistent that for most of human history, it felt natural to assume space and time were fundamentally different things. Spacetime challenges that assumption. In this view, every event is described not just by where it happens, but also by when it happens, and these descriptions cannot be fully separated. An event is a point in space-time, defined by 3 spatial coordinates and 1 time coordinate. Together, they locate the event within the universe. This idea becomes necessary once we accept that measurements of space and time depend on motion. If 2 observers are moving differently, they may disagree on distances and durations. What one observer measures as a long distance, another may measure as shorter. What one observer experiences as a longer time interval, another may experience as shorter. Spacetime provides a single framework that accounts for these differences consistently. An important detail is that spacetime is not just a bookkeeping tool. It has physical meaning. Distances in spacetime determine what can influence what. The structure of spacetime sets limits on cause and effect. It tells us which events can be connected by signals and which cannot, no matter how advanced the technology. One calm way to think about spacetime is as a map of all possible events, rather than a stage that exists independently of them. Instead of imagining space as empty and time as flowing through it, spacetime treats events as primary. Space and time emerge from how events relate to one another. Still, this idea remains abstract. We do not sense spacetime directly. We sense clocks ticking and objects moving. Our brains convert physical processes into experiences of duration and distance. Spacetime itself stays in the background, inferred through careful measurement and mathematics. This gap between description and experience is part of why spacetime feels elusive. The equations describe relationships precisely, but they do not translate easily into mental pictures. When we try to imagine spacetime, we often rely on metaphors like fabric or grids. These metaphors can help, but they are always incomplete. Another source of confusion is that spacetime treats time more like space than we are comfortable with. In the equations, time is a dimension, similar to spatial ones, though with important differences. This challenges the everyday sense that time is something special, something that flows, while space simply sits there. Physicists accept spacetime because it works. It explains motion, gravity, and light with remarkable accuracy. But accepting a framework is not the same as feeling at home in it. Spacetime remains a concept we use successfully, even as it resists becoming fully intuitive. As we continue, we will look at how this idea replaced older views and why it solved certain problems while quietly creating new ones. Understanding spacetime begins with defining it carefully, even if that definition already stretches the limits of how we naturally think. Before spacetime entered physics, space was treated as something solid and dependable, even if it was invisible. In classical physics, space was thought of as a fixed three-dimensional stage. Objects moved through it, forces acted within it, but space itself never changed. It was simply there, providing a stable backdrop for everything else. This idea came most clearly from Isaac Newton's view of the universe. In Newtonian physics, space was absolute. That meant it existed independently of the objects inside it. Even if the universe were empty, space would still remain. Distances between points were always the same, regardless of who measured them or how they were moving. This picture worked extremely well for everyday situations. When you walk across a room, throw a ball, or watch the planets move slowly across the sky, the rules of classical space describe what happens with impressive accuracy. Engineers could build bridges, astronomers could predict eclipses. Nothing seemed to demand a deeper explanation. Because it worked so reliably, this view of space felt obvious. It matched human intuition. We experience space as something steady and unmoving. Rooms do not stretch when we walk through them. Distances between landmarks feel fixed. Our senses reinforce the idea that space is simply there. In classical physics, motion was defined relative to space itself. An object could be truly at rest or truly moving, depending on how it changed position within this absolute space. Even if no other objects were nearby, motion still had meaning. Space acted like a universal reference. This assumption quietly shaped how scientists thought for centuries. When experiments were performed, space was assumed to be neutral and passive. Forces caused motion, space merely recorded it. There was no reason to think space could bend, stretch, or respond to matter in any way. Yet even within this successful framework, subtle tensions existed. Certain observations about light and motion began to raise questions. As measurements became more precise, physicists noticed that space did not behave exactly as expected when very high speeds were involved. The old assumptions started to feel slightly strained. Still, for a long time, there was no urgency to replace the classical view. The gaps were small, and the successes were enormous. Space, as a fixed container, was one of the most stable ideas in science. Understanding this older picture matters because it shows how radical the later shift would be. Einstein did not merely adjust a few details. He removed the idea of absolute space entirely. What had seemed like the most reliable part of physics turned out to be an approximation, valid only under limited conditions. As we move forward, keep in mind how natural and intuitive the classical view of space felt. The difficulty of understanding spacetime today is partly rooted in how deeply this older picture still influences the way we think. Just as space was once thought to be fixed and absolute, time was treated as universal and uniform. In classical physics, time flowed at the same rate everywhere, for everyone. There was one cosmic clock ticking steadily in the background of the universe, marking the same seconds and minutes no matter where you were or how you moved. This idea felt deeply natural. Human experience strongly supports it. We share calendars, schedules, and clocks. When two people compare watches, they expect them to agree. The assumption that time passes identically for all observers fits everyday life so well that it rarely feels like an assumption at all. In Newton's framework, time existed independently of space and matter. It did not depend on motion, gravity, or observation. Events happened in time, but time itself was unaffected by them. Even if nothing occurred, time would still pass. It was an invisible river flowing uniformly from the past into the future. Because time was universal, simultaneity was straightforward. If two events happened at the same moment, they happened at the same moment for everyone. There was no ambiguity. A now was shared across the universe. This made cause and effect easy to organize and understand. Classical mechanics relied on this idea heavily. Velocities were defined as distance traveled per unit time. Accelerations depended on how velocities change with time. These definitions only make sense if time is the same for all observers, and because they worked so well, there was little motivation to question them. Even early experiments with clocks reinforced this view. Mechanical clocks, pendulums, and later atomic clocks all seemed to tick steadily and predictably. Small variations could be blamed on imperfections, not on time itself behaving differently. Yet, as with space, subtle cracks began to appear. Studies of light revealed something strange. Its speed appeared constant, no matter how the observer moved. To make sense of this, physicists had to reconsider how time was measured. If the speed of light was fixed, something else had to give. Still, before Einstein, these ideas remained at the edges of physics. Time was assumed to be stable, external, and beyond influence. It was a background parameter, not a participant in physical processes. Understanding this older concept of time helps explain why space-time remains difficult to accept. Letting go of universal time means letting go of a shared now, something deeply tied to how we communicate, coordinate, and experience life. As we continue, we will see how Einstein brought space and time together, not as separate backgrounds, but as intertwined aspects of a single structure. That union would change both concepts forever. The major change came when Albert Einstein reconsidered the foundations of space and time together. Rather than treating them as separate, absolute backgrounds, he asked what must be true if the laws of physics are the same for all observers, and if the speed of light is constant for everyone, regardless of motion. From these calm but radical assumptions, a new picture emerged. Space and time could no longer remain independent. Measurements of distance depended on how time was measured, and measurements of time depended on how space was measured. The two became inseparably linked. In this new framework, observers moving relative to one another would not agree on lengths or durations. A moving clock would tick more slowly compared to a stationary one. A moving object would appear shortened in the direction of motion. These effects are not illusions or measurement errors. They're real physical consequences of how space-time is structured. What changed most dramatically was the idea of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another. There is no longer a single universal present moment shared by everyone. Instead, each observer carries their own slice of time through space-time. This was not a philosophical claim, it was a physical necessity. Without it, the speed of light could not remain constant across all frames of motion. Space-time adjusted itself so that light's behavior remained consistent. Later, Einstein extended these ideas further in general relativity. Gravity was no longer treated as a force acting through space. Instead, mass and energy altered the geometry of space-time itself. Objects followed curved paths because space-time around them was curved. This shift solved several problems at once. It explained the precise motion of planets. It accounted for subtle shifts in Mercury's orbit that classical physics could not explain. It predicted new phenomena like the bending of light near massive objects, which were later observed. Despite its success, the Einstein shift came at a cost. The universe became harder to picture. Space was no longer a rigid stage. Time was no longer universal. Together they formed a dynamic structure that responded to matter and motion. We gained powerful equations and precise predictions, but lost the comfort of familiar intuition. Space-time became something we could calculate accurately, yet struggle to imagine clearly. This trade-off lies at the heart of why space-time still feels poorly understood. The theory works extraordinarily well, but it asks us to abandon deeply rooted ways of thinking. As we move forward, we will explore how space-time behaves under this new view and why that behavior remains difficult to fully grasp. One of the most unfamiliar ideas introduced by Einstein is that gravity is not a force in the usual sense. Instead of objects being pulled through space by gravity, general relativity describes gravity as the shape of space-time itself. Mass and energy change the geometry of space-time, and objects move along paths determined by that geometry. In this view, space-time behaves less like an empty container and more like a structured system with measurable properties. Distances and time intervals are not fixed. They depend on how space-time is curved in a given region. The presence of a planet, a star, or a galaxy subtly alters the space-time around it. A calm way to understand this is to think about motion without pushing or pulling. If space-time is curved, then the straightest possible path through it may appear curved when viewed from within. Objects are not being forced off course, they are simply following the natural paths available to them. This explains why planets orbit stars without requiring a traditional gravitational force. The planet follows a path through curved space-time created by the star's mass. From the planet's perspective, it is moving naturally. From our perspective, the motion looks like an orbit. Time is also affected by this geometry. Near massive objects, time passes more slowly compared to regions farther away. This is not a psychological effect or a mechanical failure of clocks. It is a property of space-time itself. Clocks in different gravitational environments genuinely measure different amounts of time. This geometric description has been tested repeatedly. Atomic clocks placed at different heights on Earth tick at slightly different rates. Satellites must correct for this effect to function properly. These measurements confirm that space-time geometry influences time directly. Despite this success, geometry is an abstract language. Most of us are comfortable with shapes in 2 or 3 dimensions, but space-time geometry involves 4 dimensions and non-Euclidean rules. Curvature does not behave the way it does on flat surfaces. Parallel lines may converge or diverge. Distances change depending on the path taken. Because of this, space-time geometry is easier to calculate than to imagine. We can write equations that describe curvature precisely, but forming a clear mental picture remains difficult. Diagrams help, but they are always simplified shadows of the real structure. This gap between mathematical clarity and intuitive understanding deepens the sense that space-time is not fully understood. We know how to work with its geometry, but we still struggle to feel what that geometry truly means. As we continue, we'll see how well this geometric view works, and where its limits begin to appear. Despite how strange space-time sounds, the theories built around it perform with remarkable accuracy. Relativity has passed every major experimental test placed before it. This success is one reason physicists trust the framework, even while admitting that its deeper meaning remains unclear. One everyday example comes from satellite navigation. GPS satellites orbit Earth at high speeds and experience weaker gravity than clocks on the ground. Both effects change how time flows for those clocks. If space-time were not accounted for, GPS positions would drift by kilometers each day. The system works only because relativity predicts exactly how space-time affects time and distance. Astronomy offers another calm confirmation. The motion of planets, the bending of light around stars, and the precise timing of pulsars all align with space-time predictions. When physicists calculate how space-time should curve in these environments, observations follow the equations closely. Gravitational waves provide one of the most striking examples. When massive objects like black holes collide, they send ripples through space-time itself. These ripples travel across the universe and reach Earth, where detectors can measure them. What is being detected is not matter or light, but changes in space-time geometry. These successes show that space-time is not a speculative idea. It is a working description of reality. The equations do not just approximate behavior, they describe it with extraordinary precision across vast ranges of scale. Yet success in prediction does not guarantee clarity and understanding. Many physicists can use the equations expertly, while admitting they do not have a simple answer to what spacetime is. The theory tells us how spacetime behaves, not why it exists in this form. There is also a difference between local understanding and global understanding. Relativity works well in many specific situations, but when applied to extreme conditions, questions begin to accumulate. Near black holes at the beginning of the universe, or at extremely small scales, the theory's confidence begins to fade. This combination of strength and uncertainty is unusual. Space-time theory is not broken, but it feels incomplete. It is like a map that accurately guides travelers across familiar terrain, yet becomes less detailed at the edges. This is part of why space-time remains difficult to fully grasp. We trust it because it works. We question it because it may not be the final description. As we move forward, we will begin to explore where understanding starts to fade, even as predictions remain strong. Even though relativity works extremely well, there's a quiet point where understanding begins to thin out. This does not happen suddenly. There is no single experiment that fails or clear contradiction that appears. Instead, the difficulty shows up as a growing distance between what the equations tell us and what we can meaningfully explain. Physicists can calculate how space-time bends, stretches, and evolves with impressive accuracy. They can predict outcomes to many decimal places. But when asked what space-time is, beyond its mathematical description, answers become less precise. The theory describes relationships, not substance. One reason for this is that space-time is defined operationally. We define it through measurements: how clocks tick, how rulers behave, how light travels. Space-time is inferred from these behaviors rather than directly observed. We never measure space-time itself. We measure the motion of objects and signals within it. This works well for prediction, but it leaves open questions. Is space-time something physical, like a medium? Or is it a relational structure that only exists because events relate to one another? The equations remain silent on this point. They function without committing to an answer. Another source of fading understanding comes from abstraction. The mathematics of space-time uses advanced geometry that does not translate easily into ordinary intuition. Even trained physicists often rely on symbolic manipulation rather than mental imagery. The understanding becomes procedural rather than conceptual. This creates a subtle discomfort. In many areas of science, intuition grows alongside equations. Over time, models become easier to picture. With space-time, the opposite often happens. The more accurately it is described, the harder it becomes to imagine. There is also the issue of limits. Relativity assumes space-time is smooth and continuous, but this assumption has never been tested at extremely small scales. We do not know whether space-time remains smooth all the way down, or whether it has a different structure at the smallest levels of reality. At this boundary, understanding does not fail loudly, it simply becomes incomplete. The theory continues to function, but questions remain unanswered. This quiet incompleteness is one of the reasons space-time still feels mysterious. As we move forward, we will look at how human intuition contributes to this difficulty, and why our everyday experience may not be well suited to understanding space-time at all. Human intuition evolved to handle a narrow range of experiences. We move slowly compared to the speed of light. We live in weak gravitational fields. Distances and times in daily life are moderate and familiar. Within this range, space feels stable and time feels uniform. Space-time behaves very gently under these conditions. Relativistic effects are present, but they are extremely small. Time dilation and length contraction exist, but they are far below what we can notice without precise instruments. As a result, our brains build an internal model of the world that assumes space and time are absolute. This internal model works well for survival. It helps us navigate environments, coordinate with others, and predict motion accurately enough. There was no evolutionary advantage to sensing space-time curvature or time dilation. Those effects only become significant far outside the conditions humans evolved in. Because of this, space-time concepts feel unnatural. When we hear that time can slow down, or that distances can shrink, the ideas conflict with deeply ingrained expectations. Even when we understand the equations, our intuition resists. Scale adds another layer of difficulty. Space-time effects become important at very large scales, like galaxies and the universe as a whole, and at very small scales, like subatomic particles. Human experience sits in the middle. We are poorly positioned to directly sense either extreme. This mismatch means that space-time understanding relies heavily on instruments and mathematics. Telescopes, particle detectors, and atomic clocks extend our senses. Equations organize the data they collect, but the understanding remains indirect. There is also a psychological factor. We often try to visualize space-time as something we can step back and look at, but there is no external viewpoint. Any observer is embedded within space-time. This limits how we can imagine it. As a result, space-time understanding becomes layered. We understand how it behaves in specific situations. We understand how to calculate outcomes. But the overall picture remains fragmented. This is not unique to space-time, but it is especially pronounced here. The combination of extreme scales and limited intuition makes space-time one of the hardest concepts to internalize. As we continue, we will see how this difficulty deepens when we examine how time behaves differently for different observers. One of the most challenging ideas in space-time physics is that time does not pass at the same rate for everyone. This is not a matter of perception or faulty clocks. It is a physical effect that arises naturally from how space-time is structured. When an object moves at high speed, time passes more slowly for it compared to an object at rest. This effect, known as time dilation, has been confirmed many times. Clocks on fast-moving aircraft tick slightly more slowly than clocks on the ground. Particles created in the upper atmosphere survive longer than expected because they are moving so quickly relative to Earth. Gravity also affects time. Near a massive object, time flows more slowly than it does farther away. This means that two identical clocks placed at different heights in a gravitational field will disagree. The clock closer to the massive object will measure less time passing. These effects are small in everyday life, but they are real. They accumulate steadily. Over long periods or extreme conditions, the differences become significant. In principle, two people could age at different rates if they experience different paths through space-time. This challenges the idea of a universal present. If time flows differently in different places and for different observers, there is no single now that applies everywhere. Each observer carries their own timeline shaped by motion and gravity. This does not lead to contradictions, but it does lead to complexity. To compare events, we must specify who is measuring and how. Space-time provides the framework to do this consistently, but it requires abandoning simple assumptions. The difficulty here is not mathematical. The equations describing time dilation are straightforward. The difficulty is conceptual. Our everyday language assumes a shared time. Our experiences reinforce that assumption. Spacetime asks us to let go of it. This is another reason spacetime remains hard to understand. It behaves consistently, but not in the way we naturally expect. As we continue, we will see that space itself also loses its familiar simplicity. In the classical view, space was treated as an empty stage where events occurred. In space-time physics, space is no longer passive. It has structure, and that structure can change. Space can stretch, compress, and carry disturbances, all as part of the broader behavior of space-time. One of the clearest demonstrations of this is the expansion of the universe. Galaxies are not simply moving through space away from each other. Instead, space itself is expanding between them. Over vast distances, this expansion becomes measurable, changing how light travels and how structures evolve. Another example comes from gravitational waves. When massive objects accelerate, especially in violent events like black hole mergers, they send ripples through space-time. These ripples travel at the speed of light and gently stretch and compress space as they pass. Detectors on Earth measure these changes directly. This means space is not an inert backdrop. It participates in physical processes. It responds to energy and motion. In some sense, space has dynamics, governed by precise equations. Yet, despite this activity, space has no substance in the ordinary sense. It does not have atoms or particles. We cannot scoop it up or isolate it. Its properties are defined by how distances and times behave, not by what it is made of. This creates a conceptual tension. Space acts like something real and physical, but it lacks the familiar qualities of physical objects. It is neither a material nor merely an abstract idea. It occupies an unusual category in our understanding. Diagrams often depict space as a grid or fabric to make these ideas more accessible. These images help illustrate curvature and waves, but they are metaphors. They should not be taken literally. Space is not a sheet floating in a higher dimension. Recognizing these limits is important. Metaphors can clarify, but they can also mislead. When we rely too heavily on them, we may think we understand space-time more deeply than we do. As we move forward, we will look at why visualizing space-time remains such a challenge, and how this limits intuitive understanding even as mathematical descriptions remain strong. Human understanding relies heavily on visual intuition. We like to picture how things work. For space-time, this becomes a serious limitation. The structures involved are four-dimensional, curved, and dynamic, while our intuition is built for three-dimensional, mostly flat environments. Most visual representations of space-time reduce it to 2 or 3 dimensions. Grids bending under weight, rubber sheets stretching, or lines curving around objects are common examples. These images can illustrate certain relationships, but they hide just as much as they reveal. One problem is that curvature in space-time is not curvature into some higher space. It is an intrinsic property. Distances and angles change within space-time itself. Our diagrams often suggest an external dimension, which does not exist in the theory. Another issue is time. We can draw spatial dimensions easily, but time behaves differently. We experience it as a flow, not as a direction we can move freely. When time is drawn as a dimension, it does not behave like the others. This makes visual analogies unstable. Because of this, physicists rely more on equations than pictures. The mathematics of space-time captures relationships precisely without requiring visual interpretation. This is powerful, but it shifts understanding into a symbolic domain. For students and even experienced researchers, this can feel unsatisfying. One can manipulate equations correctly while lacking a clear mental image of what is happening. The understanding becomes functional rather than intuitive. This problem is not a failure of education. It reflects a deeper mismatch between how space-time behaves and how human cognition evolved. We're trying to picture something that was never meant to be pictured directly. As a result, space-time understanding often comes in layers. At one layer, the equations are clear. At another, the intuition remains incomplete. Both layers coexist. This layered understanding contributes to the sense that space-time is not fully grasped. We can describe it, use it, and test it, but seeing it clearly in the mind remains difficult. Next, we will explore how the very number of dimensions adds to this challenge. Space-time is described as having 4 dimensions, 3 of space and 1 of time. This statement alone introduces difficulty. Human experience is grounded in 3 spatial dimensions, and even those are understood through movement and touch, not abstraction. A dimension in physics is simply a way to specify location. In space-time, an event requires 4 numbers to be fully described. 3 tell us where it happens, 1 tells us when. Mathematically, this is straightforward. Experientially, it is not. We do not move through time the way we move through space. We cannot step backward or sideways in time. We cannot choose a direction. Time has a built-in orientation. This asymmetry makes time feel fundamentally different, even though it is treated as a dimension in the equations. This difference leads to confusion. When physicists say time is a dimension, they do not mean it is interchangeable with space. The mathematical structure treats it differently. Distances in space-time involve a combination of spatial and temporal intervals, with time contributing in a unique way. Still, grouping time with space challenges everyday understanding. It suggests that past, present, and future events all exist within the space-time structure, even if we experience them sequentially. This idea can feel unsettling, even when stated calmly. Another complication is that higher dimensional thinking is unfamiliar. We struggle to imagine even 4 dimensions, let alone more. Yet some theories suggest that space-time may have additional dimensions that are hidden or compact. Whether or not these extra dimensions exist, the difficulty remains. Our intuition resists dimensional descriptions that go beyond direct experience. This resistance does not make the theory wrong, but it does limit our sense of understanding. Dimensions in space-time physics are tools. They organize relationships between events, they allow equations to work, but they do not come with built-in imagery. As we continue, we will see how one particular feature of space-time, the speed of light, plays a central role in shaping these dimensions and setting the structure of reality itself. In space-time physics, the speed of light is not just a property of light, it is a fundamental feature of how space-time itself is organized. It sets the maximum speed at which information, energy or influence can travel. This limit is the same for all observers, regardless of how they move. No matter how fast an observer is traveling, they will measure light moving at the same speed. This constancy is what forces space and time to adjust. Distances and durations change so that the speed of light remains fixed. Because of this, the speed of light defines the structure of cause and effect. Events can only influence other events if a signal travelling at or below this speed can connect them. If no such path exists, the events are causally disconnected. This idea reshapes how we think about simultaneity. Two events that appear to happen at the same time for one observer may not be simultaneous for another. What matters is whether a signal could travel between them. The speed of light also links space and time numerically. Time can be converted into distance by multiplying by this speed. This allows space and time to be combined into spacetime intervals that remain the same for all observers. This invariance is central to spacetime. It provides a stable structure amid changing measurements. While observers may disagree on distances and durations, they agree on spacetime intervals. Yet, despite its central role, the speed of light remains conceptually strange. Why does this limit exist? Why does spacetime enforce it? The theory does not explain these questions. It simply describes their consequences. This is another example of spacetime being well-defined operationally but poorly explained fundamentally. We know what it does. We do not fully know why it is this way. As we move on, we will see how this limit organizes spacetime into regions of possible and impossible influence, shaping the flow of cause and effect itself. Once the speed of light sets a limit, spacetime becomes naturally organized into regions of influence. Not everything can affect everything else. Some events are connected by cause and effect, while others are forever isolated from one another. Physicists describe this using the idea of light cones. From any event, imagine all the possible paths a light signal could take as it moves forward in time. These paths form a cone-like structure in spacetime. Any event inside this future cone can, in principle, be influenced by the original event. Any event outside it cannot. There is also a past light cone. This includes all events that could have influenced the original one. Together, these cones define the causal structure of spacetime. They tell us what can be connected, and in which direction influence can flow. This structure replaces older, simpler ideas of causality. In classical physics, cause and effect were ordered by a universal time. If one event happened earlier, it could cause a later one. In spacetime, the situation is more subtle. The ordering of events can depend on the observer, as long as no causal connection is possible between them. This means that some events do not have a definite order for all observers. One observer may say event A happened before event B, another may say the opposite. As long as no signal could travel between them, both descriptions are valid. This does not lead to paradoxes, but it does challenge intuition. We're used to thinking of time as a single sequence that orders everything. Spacetime replaces that with a network of local causal relationships. Within this network, cause and effect remain solid. Signals do not travel backward in time. Influences do not exceed the speed of light. The structure is strict, even if it is unfamiliar. Understanding this causal structure is essential for modern physics. It underlies everything from particle interactions to the evolution of the universe. Yet it remains difficult to internalize because it replaces a simple global order with a more complex local one. As we continue, we will see how this carefully ordered spacetime picture begins to face serious challenges when quantum physics enters the scene. So far, spacetime has been described using relativity, a theory that works smoothly at large scales. But nature has another framework that is just as successful: quantum physics. Quantum theory describes atoms, particles, and fields with extraordinary precision, and this is where a deep tension begins to appear. Quantum physics treats reality as inherently fluctuating. Particles do not have precise positions and velocities at the same time. Fields are never truly calm. Even in what we call empty space, quantum fields are active, constantly shifting at very small scales. This view contrasts sharply with the smooth spacetime of relativity. In general relativity, space-time is continuous. It can curve, stretch, and ripple, but it does so smoothly, without breaks or jumps. The geometry is well defined at every point. When physicists try to describe space-time using quantum rules, problems arise. The mathematics becomes unstable. Quantities grow without bound. Predictions stop making sense. This suggests that space-time, as described by relativity, may not survive unchanged at very small scales. The difficulty is not just technical, it is conceptual. Quantum physics assumes a fixed background of space and time in which particles interact. Relativity says space-time itself is dynamic and shaped by those interactions. Each theory relies on assumptions the other does not share. This creates a circular problem. To apply quantum rules, we need space-time. To describe space-time fully, we may need quantum rules. Neither framework comfortably contains the other. This conflict shows up most clearly at extreme scales, such as near black holes or at the earliest moments of the universe. In these environments, gravity is strong and quantum effects are unavoidable. Our current theories cannot describe them together consistently, yet both theories work exceptionally well in their own domains. Relativity explains gravity and cosmic structure. Quantum physics explains atoms, chemistry, and technology. The problem is not that either theory is wrong, but that they are incomplete when taken alone. This is a major reason we still do not understand space-time. Our best description of it breaks down precisely where we expect the deepest answers to lie. As we move forward, we will examine specific ways this conflict shows itself, beginning with how quantum fields differ from smooth space-time geometry. In quantum physics, the fundamental ingredients of reality are not solid objects moving through empty space. Instead, they are fields that exist everywhere. Each type of particle is associated with a field, and particles appear as excitations or disturbances within those fields. These quantum fields are never completely still. Even in the lowest energy state, they fluctuate. This restless behavior is not noise or error, it is built into the structure of the theory. At very small scales, uncertainty is unavoidable. General relativity, by contrast, treats space-time as smooth and well-defined. At every point, distances and time intervals can be calculated precisely. Curvature changes continuously from place to place. There are no sudden jumps or intrinsic fluctuations in the geometry itself. When these two pictures are combined, tension arises. If quantum fields fluctuate, they carry energy. Energy affects space-time curvature. If space-time responds to these fluctuations, then its geometry should also fluctuate. But the mathematics of general relativity is not designed to handle this kind of behavior. Attempts to calculate these effects lead to infinities. The equations produce results that grow without limit and lose physical meaning. This signals that something essential is missing from the description. One possibility is that space-time is not truly smooth at the smallest scales. It may have a different structure that only appears continuous when viewed from far away, much like a surface that looks smooth until examined closely. Another possibility is that space-time itself emerges from quantum interactions, rather than existing as a fundamental entity. In this view, smooth geometry is an approximation that breaks down under extreme conditions. At present, there is no experimental evidence to decide between these possibilities. The scales involved are far beyond current technology. We are left with mathematical hints and conceptual gaps. This unresolved conflict between quantum fields and smooth space-time geometry is one of the central reasons space-time remains poorly understood. It works beautifully in calm conditions, but becomes uncertain when pushed to its limits. As we continue, we will focus on one of those limits, the extremely small distances where space-time may no longer behave as a continuous structure at all. When physicists talk about the limits of space-time, they often point to an extremely small scale known as the Planck scale. This scale is far smaller than atoms, smaller even than protons. It represents a distance and a time so tiny that our current theories stop giving reliable answers. At the Planck scale, quantum effects and gravity become equally important. This is unusual. In most situations, gravity is either dominant, as in stars and galaxies, or negligible, as in atomic physics. At this tiny scale, neither can be ignored. The problem is that general relativity assumes space-time can be divided into arbitrarily small pieces. You can zoom in as much as you like, and the geometry remains well defined. Quantum physics, however, places limits on how precisely things can be measured. Energy fluctuations grow as we probe smaller regions. When we try to measure space-time itself at extremely small scales, the energy required becomes so large that it would significantly distort the space-time being measured. The act of observation interferes with the object of observation in a fundamental way. This leads to a kind of measurement paradox. To understand space-time at the smallest scales, we would need probes of extremely high energy, but those probes would create strong gravitational effects, possibly forming tiny black holes and destroying the very structure we are trying to study. As a result, the Planck scale appears to be a boundary beyond which our usual concepts of space and time lose meaning. Distances may no longer be smooth, time may no longer flow in a continuous way. The familiar structure of space-time could dissolve into something more fundamental, yet we do not know what replaces it. There is no direct experimental access to this scale. All our ideas about it come from theoretical reasoning and mathematical consistency, not observation. Some physicists suggest that space-time becomes discrete at this scale, made of tiny units rather than a smooth continuum. Others suggest that space-time is not a thing at all at this level, but an emergent pattern arising from deeper quantum relationships. What makes this especially difficult is that both possibilities challenge our basic assumptions. We're used to thinking of space and time as always present, always available. The Planck scale hints that this may not be true. This does not mean our current theories are useless. Far from it. They work exceptionally well above this scale, but it does mean that space-time, as we understand it, may be an approximation rather than a final description. This realization is unsettling, but also motivating. It suggests that space-time is not the deepest layer of reality. It is something that emerges, behaves, and fades depending on scale. As we move on, we will explore a related question: whether space-time is truly continuous at any scale, or whether its smooth appearance hides a more granular underlying structure. For centuries, space and time were assumed to be continuous. You could always divide a distance in half, then in half again, without reaching a smallest unit. Time could be sliced into ever shorter intervals without limit. This assumption is deeply built into classical physics and everyday thinking. General relativity follows this tradition. Its equations assume that space-time can be described smoothly at every scale. Curvature changes gradually. Points lie arbitrarily close together. There is no smallest length or shortest time built into the theory itself. Quantum physics, however, has already shown that some quantities are not continuous. Energy comes in discrete levels. Certain properties change in jumps rather than smoothly. This raises the question of whether space-time itself might also be discrete at a fundamental level. If space-time were made of tiny units, much like matter is made of atoms, its smooth appearance could be an illusion that emerges only at large scales. At very small scales, space-time might behave more like a network or lattice than a continuous surface. There is no direct evidence for this yet. Any discreteness would appear at scales far smaller than we can currently probe, but theoretical arguments suggest that assuming perfect continuity may lead to inconsistencies when gravity and quantum physics are combined. On the other hand, discreteness brings its own challenges. How do you define motion, curvature, or causality on a discrete structure? How does a smooth space-time emerge from something granular? These questions are difficult and remain unresolved. Some approaches to quantum gravity propose specific discrete structures. Others preserve continuity but modify the rules. Still others suggest that space-time is neither continuous nor discrete in the usual sense, but something more abstract. What all these ideas share is uncertainty. We do not yet know whether continuity is a fundamental property of space-time or a useful approximation. This uncertainty keeps space-time firmly in the category of not fully understood. For now, continuity remains a working assumption. It allows calculations to proceed and predictions to be made. But physicists remain open to the possibility that this assumption will eventually be replaced. As we continue, we will focus on one particular force that makes space-time especially difficult to understand at a fundamental level: gravity itself. Among the fundamental forces of nature, gravity stands apart. It is the weakest force by far, yet it governs the large-scale structure of the universe. It shapes planets, stars, galaxies, and the overall evolution of cosmic space. This unique role makes gravity central to the mystery of space-time. In general relativity, gravity is not something that exists within space-time. It is space-time behavior. Curvature, motion, and time flow are all expressions of gravity acting through geometry. This makes gravity inseparable from space-time itself. Quantum physics treats forces very differently. Other forces are described through particles and fields operating within a fixed space-time background. Gravity resists this approach. When physicists try to treat gravity like the other forces, the mathematics becomes unstable. One reason is gravity's universality. Every form of energy and mass contributes to space-time curvature. There is no way to isolate gravity from the system being studied. Any attempt to probe space-time at small scales necessarily involves gravity as part of the measurement. Another issue is gravity's weakness. Because it is so weak, quantum effects of gravity only become noticeable at extremely high energies or extremely small distances. This puts them far beyond current experimental reach, leaving theory without direct guidance from observation. This combination of weakness and universality is unusual. It makes gravity difficult to study experimentally and difficult to describe theoretically. Yet it cannot be ignored, because it defines space-time itself. As a result, gravity becomes the main obstacle to understanding space-time at a fundamental level. Other forces fit comfortably within quantum frameworks. Gravity does not. Until this mismatch is resolved, space-time remains only partially understood. This does not mean progress has stalled, it means the problem is deep. Gravity sits at the boundary between what we can calculate and what we can conceptually explain. Next, we will see how black holes push this problem to its limits, revealing where our current understanding of space-time begins to break down most clearly. Black holes are not just exotic objects in space. They act as natural experiments that push space-time to its limits. In their presence, gravity becomes extreme, and the assumptions behind our theories are tested in the most demanding conditions. According to general relativity, a black hole forms when a large amount of mass is compressed into a very small region. The curvature of space-time becomes so strong that nothing, not even light, can escape from within a certain boundary. This boundary is called the event horizon. Outside the event horizon, space-time behaves in ways we can calculate and predict. Orbits, light paths, and time dilation all follow the equations closely. Inside the horizon, however, the theory leads us toward regions where curvature grows without bound. These regions challenge our understanding. As matter falls inward, space-time curvature increases dramatically. Time and space effectively trade roles. Paths that once led forward in time now lead inward, toward the center. This behavior has no parallel in everyday experience. Black holes also force us to confront the limits of observation. The event horizon hides information from the outside universe. Once something crosses it, we can no longer track what happens next using direct measurement. Space-time becomes partially inaccessible. This makes black holes ideal stress tests for our theories. They are simple in one sense, defined by mass, charge, and rotation, but extreme in their effects. They expose where general relativity remains silent or produces unclear answers. Quantum physics adds further tension. Near the event horizon, quantum effects become important. Particles and radiation appear where classical theory predicts emptiness. This suggests that space-time near black holes cannot be fully described by smooth geometry alone. Despite decades of study, black holes remain places where our understanding of space-time feels provisional. The equations guide us, but they do not give a complete story. Black holes show us that space-time works until it doesn't, and that boundary is precisely where understanding becomes most uncertain. As we continue, we will look more closely at what happens when space-time descriptions break down entirely. Beginning with the idea of singularities. At the center of a black hole, general relativity predicts something called a singularity. This is not an object in the usual sense. It is a point where the equations themselves stop working. Quantities like density and curvature grow without limit, and space-time, as described by the theory, breaks down. In physics, infinities are usually a warning sign. They do not mean that something is truly infinite in nature. They mean that the model being used is no longer adequate. When a theory produces infinities, it is telling us that it has reached the edge of its applicability. Singularities appear not only in black holes, but also when we trace the universe back to its earliest moments. The equations suggest that space-time began in a state of infinite density and curvature. This again signals a breakdown, not a complete explanation. The problem is that singularities are places where space-time itself seems to lose meaning. Distances shrink to zero. Time, as described by the equations, comes to an end. There is no way to extend the description further using current theories. This is deeply unsettling, because space-time is supposed to be the framework within which physics operates. If space-time breaks down, so does our ability to describe events, causes, and outcomes. Most physicists do not believe singularities are real features of the universe. Instead, they are seen as indicators that a deeper theory is needed. A theory that includes quantum effects of gravity may smooth out these infinities, replacing singularities with something finite and well-defined. However, without such a theory, we're left with gaps. We can describe how space-time behaves up to the edge of a singularity, but not beyond it. The most extreme regions of the universe remain hidden behind mathematical failure. This is another reason we say we do not fully understand space-time. At precisely the points where gravity is strongest and the structure of space-time matters most, our best descriptions fall silent. As we continue, we will examine how time itself behaves in these extreme conditions, and why its role becomes especially uncertain near the limits of space-time. Near extreme gravitational environments such as black holes, time behaves in ways that challenge even the relativistic picture we have built so far. According to general relativity, as an object approaches a region of very strong gravity, time slows down relative to distant observers. This effect becomes more pronounced the closer one gets to the event horizon. From the perspective of a distant observer, an object falling toward a black hole appears to slow, fade, and never quite cross the horizon. Its clock seems to tick more and more slowly. This is not an illusion caused by light delays alone. It reflects how space-time itself is structured near extreme gravity. From the perspective of the falling object, however, time continues to pass normally. The object crosses the event horizon without noticing anything special at that exact boundary. This difference in description is not a contradiction. It reflects the fact that time is no longer a shared quantity between observers in strongly curved space-time. Inside the horizon, the situation becomes even stranger. According to the equations, the direction we usually think of as time becomes aligned with the inward direction toward the center. Moving forward in time means moving deeper inward. Avoiding the center becomes as impossible as stopping time. This breakdown of familiar roles shows how deeply time is tied to space-time geometry. Time is not an external parameter ticking independently. It is shaped by curvature, motion, and gravity. In extreme cases, its behavior departs radically from everyday expectations. The problem is that we cannot test these predictions directly. The interior of a black hole is hidden from observation. We rely entirely on mathematical extrapolation. This makes it difficult to say whether time truly behaves this way or whether new physics alters the picture. Once again, we encounter a familiar pattern. Space-time theory gives us precise predictions up to a boundary, then asks us to continue beyond where verification is possible. Understanding becomes tentative. This uncertainty about time under extreme conditions reinforces the broader point. Space-time works well where gravity is moderate and observations are possible. Where gravity is strongest, time itself becomes unclear. Next, we will explore another tension tied to black holes and space-time, the question of information and whether space-time allows it to be lost. One of the most persistent problems tied to space-time appears when we ask what happens to information. In physics, information is not abstract knowledge. It refers to the detailed state of a system, the positions, energies, and relationships of its components. Modern physics assumes that information is conserved. It may change form, but it is never truly destroyed. Black holes challenge this assumption. When matter falls into a black hole, all the details that describe it seem to disappear behind the event horizon. From the outside, only a few properties remain visible, such as mass and rotation. Everything else is hidden. Quantum physics makes this troubling. If information is truly lost, the basic rules of quantum theory are violated. Predictions would become unreliable. Cause and effect would no longer be strictly preserved. This conflict is known as the black hole information problem. It is not a minor technical issue. It sits at the intersection of quantum theory, gravity, and space-time structure. It suggests that our understanding of space-time is incomplete at a fundamental level. One proposed resolution involves subtle radiation emitted by black holes. Over extremely long times, black holes slowly lose mass and may eventually disappear. If information is somehow encoded in this radiation, then it may not be lost after all. However, explaining how this encoding works requires space-time to behave in unfamiliar ways. Information would need to be stored at the boundary of the black hole or spread non-locally through space-time. These ideas stretch our usual understanding of locality and geometry. What makes this puzzle especially difficult is that it does not arise in ordinary situations. It only appears when space-time is pushed to extremes, yet those extremes may reveal the true nature of space-time itself. The information puzzle remains unresolved despite decades of work. It tells us that space-time, as currently understood, cannot fully account for how information behaves. Something deeper is at work. As we continue, we will look at the major attempts to resolve these issues and why none of them have yet delivered a complete understanding of space-time. Because of the deep conflicts we've explored, physicists have spent decades trying to build a more complete picture of space-time. These efforts are often grouped under the name quantum gravity, but they are not a single theory. They are a collection of approaches, each trying to resolve the same core problem from a different direction. One approach attempts to quantize space-time directly, treating its geometry as something that can exist in discrete states, much like energy levels in atoms. In these models, space-time is no longer smooth at the smallest scales. Instead, it is built from fundamental units connected in a network-like structure. Smooth space-time would then emerge only when many of these units act together. Another approach keeps space-time continuous, but introduces additional ingredients. These models suggest that new symmetries, dimensions, or mathematical structures become important at very small scales. Space-time remains geometric, but its geometry becomes more complex than general relativity alone allows. There are also approaches that step back and question whether space-time should be treated as fundamental at all. In these views, space-time emerges from deeper non-spatial relationships. Geometry and distance appear only after averaging over many microscopic interactions. At the deepest level, space-time may not exist in any familiar sense. Each of these attempts has strengths. They can resolve certain mathematical problems or explain specific features, like black hole entropy or information flow. But each also faces serious challenges. Many require assumptions that cannot yet be tested. Others become mathematically complex to the point of being difficult to interpret physically. What all these efforts share is incompleteness. None have yet produced clear, testable predictions that distinguish them decisively from one another. Without experimental guidance, progress remains slow and cautious. This situation is unusual in physics. Often, experiments lead theory forward. Here, theory is running ahead, waiting for experiments that may be decades away. This leaves space-time in a state of careful uncertainty. The existence of many competing ideas is not a weakness. It reflects the depth of the problem. Space-time touches every part of physics, so changing its foundations has wide consequences. As we move on, we will examine one of the most intriguing ideas to emerge from these efforts: the possibility that space-time itself is not fundamental, but something that arises from deeper physical processes. One of the most striking ideas to come out of modern physics is that space-time may not be a fundamental ingredient of reality. Instead, it may be something that emerges from deeper physical rules, much like temperature emerges from the motion of atoms. In everyday life, temperature feels basic. Objects are hot or cold, yet temperature does not exist at the level of individual particles. It appears only when many particles interact in organized ways. Some physicists suggest space-time may be similar. At a deep level, there may be no space and no time, only relationships and interactions. spacetime would then arise as a large-scale pattern. This idea helps explain why spacetime works so well in many situations but fails at extreme scales. If spacetime is emergent, then general relativity would be an effective theory, valid only when many underlying elements act together smoothly. At very small scales, the concept itself may no longer apply. Support for this view comes from several directions. In studies of black holes, the amount of information they contain appears to scale with surface area, not volume. This hints that space-time geometry may be tied to information in an unexpected way. Other theoretical results suggest deep connections between space-time and quantum entanglement. In these ideas, the way quantum systems are correlated may determine the shape and connectivity of space-time. Geometry would then reflect patterns of information, not distances in a pre-existing space. This shifts the question dramatically. Instead of asking what is space-time made of, we begin to ask under what conditions does space-time appear. Understanding becomes less about structure and more about emergence. The challenge is that emergent explanations are subtle. They require connecting very different levels of description. We may understand the underlying rules and still struggle to see how familiar spacetime arises from them. For now, spacetime as emergent remains a promising but incomplete idea. It offers a way to reconcile quantum physics and gravity, but it also asks us to let go of the idea that space and time are fundamental. This perspective reinforces why spacetime still feels poorly understood. We may be trying to treat as basic something that is actually a consequence of deeper processes. As we continue, we will look at another line of evidence that spacetime behaves more like a physical system than a passive background. Its surprising connection to heat and thermodynamics. Another unexpected clue about the nature of spacetime comes from thermodynamics, the branch of physics that deals with heat, energy, and entropy. At first glance, thermodynamics seems far removed from geometry and gravity. Yet over time, deep connections have emerged. One of the earliest hints appeared in the study of black holes. Physicists discovered that black holes behave as if they have a temperature. They emit a faint form of radiation and slowly lose energy. This was surprising because classical spacetime geometry had no place for temperature or heat. Even more surprising was the discovery that black holes have entropy, a measure of how many internal states they can have. This entropy is proportional not to their volume, but to the area of their event horizon. This suggests that spacetime geometry encodes information in a way that resembles thermodynamic systems. These results imply that spacetime is not just geometric. It has properties usually associated with physical systems made of many microscopic parts. Temperature and entropy normally arise when many small components interact statistically. Their appearance in spacetime hints at an underlying microscopic structure. Some physicists have taken this further. They have shown that the equations of general relativity can be derived from thermodynamic principles, as if spacetime geometry emerges from rules about energy flow and entropy balance. In this view, gravity is not fundamental, but an emergent effect, similar to pressure in a gas. This perspective is powerful, but also unsettling. It suggests that spacetime behaves like a collective system, governed by statistical laws. The smooth geometry we experience would then be an average description, not a fundamental one. Yet thermodynamics does not tell us what the microscopic components of spacetime are. It only tells us that such components likely exist. We see their collective behavior, but not the underlying details. This reinforces a recurring theme. Space-time behaves consistently and predictably at large scales, but its deeper nature remains hidden. Thermodynamics gives us strong hints, but not a complete explanation. As we move on, we will return from these abstract ideas to a more grounded question: how observation itself limits what we can know about space-time from within it. Every physical theory is shaped not only by what exists, but by what can be observed. Space-time is no exception. One of the quiet difficulties in understanding space-time is that we are always observing it from within. There is no external vantage point. When we measure space or time, we do so using physical systems, clocks, rulers, signals, detectors. These tools are themselves embedded in space-time. Their behavior depends on the very structure we're trying to measure. This creates a subtle feedback loop between observer and observed. In relativity, this dependence is explicit. Measurements of distance and duration vary with motion and gravity. There is no observer-independent way to assign a single time or distance to an event. Observation becomes relational. What is measured depends on how and where the measurement is made. Quantum physics deepens this issue. At very small scales, observation affects the system being observed. Measuring energy or position disturbs the system in unavoidable ways. If space-time itself has a quantum nature, then observing space-time may disturb it as well. This raises difficult questions. Can space-time be defined independently of observers? Or is space-time, at least in part, a framework that organizes observations rather than an object that exists on its own? Physics usually resolves such questions by appealing to invariants, quantities that all observers agree on. In space-time, these include certain intervals and causal relationships. These invariants provide stability, but they do not restore a single shared picture. As a result, our understanding of space-time is partly constrained by perspective. We know how it behaves relative to observers, but we do not know how it would look from nowhere at all, if such a viewpoint even makes sense. This limitation does not weaken the science, it clarifies its scope. Space-time theory is a theory about relations between events, measurements, and observers. It is less a description of a background substance, and more a rule book for how observations fit together. Recognizing this helps explain why space-time remains elusive. It is not just difficult to imagine, it may not be something that can be fully separated from the act of observing it. As we continue, we will look at a related tension: how our equations achieve great mathematical success, while our conceptual explanations lag behind. One of the quiet frustrations in modern physics is that our equations often work better than our explanations. Space-time is a clear example of this. The mathematics of relativity is precise, elegant, and highly predictive. Yet when we try to explain what space-time is, the clarity softens. Physicists can calculate how space-time curves, how time slows, and how light travels with remarkable accuracy. These calculations lead to results that match experiments and observations again and again. In this sense, space-time is one of the most successful ideas in science. But success in calculation does not automatically lead to conceptual comfort. Many of the equations describe relationships rather than mechanisms. They tell us what happens without telling us why it happens this way. This leaves room for interpretation and uncertainty. In earlier areas of physics, conceptual understanding often followed mathematical success. Over time, atoms, fields, and forces became easier to picture. With space-time, the opposite has happened. As the mathematics has become more refined, the concepts have become more abstract. This gap is not a failure of reasoning. It reflects the possibility that space-time does not have a simple, underlying picture that fits human intuition. The equations may be the most honest description available, even if they resist translation into everyday language. There's also the issue of multiple interpretations. Different physicists may use the same equations while holding different views about what spacetime fundamentally represents. Some see it as a real physical entity. Others see it as a relational structure. The math allows both views to coexist. This situation is unusual but not unprecedented. In quantum mechanics, similar gaps exist between formalism and interpretation. Spacetime shares this characteristic, sitting at the edge of what mathematics can express clearly and what concepts can comfortably explain. Recognizing this helps temper expectations. Understanding spacetime may not mean finding a simple picture that makes everything intuitive. It may mean accepting a framework that works reliably while remaining conceptually open-ended. As we move forward, we will examine another source of difficulty, the limits of everyday language itself, and how words shape, and sometimes constrain, our understanding of spacetime. Language evolved to describe everyday experiences. We talk about before and after here and there, faster and slower. These words work well when space feels fixed and time feels shared. Spacetime stretches this vocabulary to its limits. In everyday speech, time is something that flows, space is something that contains. These metaphors are deeply embedded in how we think. When physics tells us that time can slow down or that space can expand, we instinctively imagine familiar processes behaving oddly. But spacetime is not behaving like a substance that flows or stretches. It follows mathematical relationships that do not map cleanly onto ordinary language. Terms like curvature, dimension, and fabric help bridge the gap, but they also mislead. Curvature suggests bending into something else. Fabric suggests a material surface. Dimensions suggest directions we could move through. In spacetime physics, these ideas are only partial guides. Because of this, explanations often rely on approximations. We say spacetime bends, even though nothing is bending in a material sense. We say time slows, even though nothing is mechanically changing inside the clock. These phrases point toward real effects, but they do not fully capture what is happening. This limitation of language creates a sense of mystery that is partly artificial. Some confusion comes not from spacetime itself, but from the tools we use to describe it. Words are doing their best to gesture toward relationships that are more naturally expressed in equations. Physicists are aware of this. In technical work, they rely on symbols rather than words. Language becomes secondary, used mainly to guide intuition rather than define reality precisely. For listeners and learners, these can feel unsatisfying. We want clear descriptions. We want explanations that feel complete. Spacetime resists that demand. It behaves consistently, but it does not easily submit to everyday storytelling. Recognizing the limits of language helps soften this frustration. It reminds us that understanding does not always mean verbal clarity. Sometimes it means knowing how ideas connect, even if the words remain approximate. As we continue, we will place spacetime among other mysteries in science, and see how incomplete understanding has often been a normal part of scientific progress. Spacetime is not the first concept in science to resist full understanding. Throughout history, many fundamental ideas began as useful descriptions long before their deeper nature was clarified. Recognizing this pattern can help place spacetime in a calmer context. For a long time, heat was treated as a fluid-like substance. Scientists could measure it, transfer it, and use it to do work even though they did not understand what it was made of. Only later did heat become understood as the motion of particles. The early descriptions were not wrong, they were incomplete. Light followed a similar path. At different times it was described as particles, waves, or something in between. Each description worked in certain situations and failed in others. Only gradually did a more nuanced picture emerge, and even now light resists a single, simple explanation. Electricity and magnetism also began as mysterious forces acting at a distance. Their underlying structure became clearer only after new mathematics and experiments reshaped how space and fields were understood. Progress came slowly, often through partial insights rather than sudden clarity. Spacetime may be following the same trajectory. We have a framework that works exceptionally well within its domain. We use it confidently in technology and observation, yet we sense that it is not the final story. This perspective helps reduce the tension around not understanding spacetime completely. In science, partial understanding is often the starting point, not the end. Useful theories come first. Deeper explanations follow, sometimes much later. Comparing space-time to past mysteries does not solve the problem, but it reframes it. Uncertainty becomes a sign of active exploration rather than failure. The lack of a final answer reflects the depth of the question. As we move on, we will look more closely at how uncertainty itself plays a role in science, and why admitting "we don't know yet" is often a productive position. In science, saying we do not fully understand is not a weakness. It is a precise statement about the limits of current knowledge. With spacetime, this honesty matters because the theory works extremely well while still leaving deep questions open. Physicists understand how to use spacetime. They know how to calculate motion, gravity, and time dilation. They know how to test these predictions and confirm them with experiments. What remains unclear is the deeper explanation, why spacetime has this structure, and whether it is fundamental or emergent. This situation is not unusual at the frontiers of science. Often, models are developed because they work, not because they're fully explained. Understanding grows in layers. The first layer is predictive, the next is explanatory. The deepest layer may take generations to reach. Admitting incomplete understanding keeps science flexible. It prevents ideas from becoming rigid beliefs. In the case of spacetime, this openness allows physicists to explore alternatives without discarding what already works. There's also a practical reason for this honesty. If spacetime is emergent or approximate, treating it as final could block progress. Acknowledging uncertainty keeps attention focused on where new insights are most needed. For listeners, this may feel unsettling. We often expect science to provide clear answers, but at its edges, science provides careful questions instead. Spacetime sits at one of those edges. As we continue, we will shift from this reflective pause back toward broader context, exploring how human curiosity itself fits into the ongoing effort to understand spacetime. Human curiosity did not evolve to understand spacetime. It evolved to help us survive, to notice patterns in our environment, and to predict what might happen next. Yet over time, that same curiosity expanded beyond immediate needs and began to ask questions about the structure of reality itself. Spacetime is one of those questions. It is not directly useful for finding food or avoiding danger. Instead, it arises from a deeper impulse, the desire to understand how the world holds together. This impulse has driven science forward for centuries, even when answers were slow or incomplete. What is interesting is that curiosity often runs ahead of understanding. Humans ask questions before they have the tools to answer them. This has always been true. Early astronomers asked about the motion of planets long before gravity was understood. Today, we ask about space-time long before its deepest structure is known. This pattern suggests that not understanding space-time is not a failure of intelligence. It is a natural stage in the growth of knowledge. Curiosity pushes outward. Understanding follows, sometimes slowly, sometimes unevenly. There is also something uniquely human about being comfortable with open questions. We can hold uncertainty without immediate resolution. In the case of space-time, this ability allows exploration to continue without forcing premature conclusions. Curiosity about space-time also reflects a shift in perspective. Instead of focusing only on objects and forces, we're questioning the framework that contains them. This is a sign that science has reached a mature stage, where even its foundations are open to examination. As we move forward, we will connect this curiosity to something closer to daily experience, how living systems, including our own brains, construct a sense of time that differs from physical time. While physics describes time as part of space-time, biology experiences time in a very different way. Our sense of time is not a direct measurement of physical time. It is a construction created by the brain, shaped by attention, memory, and metabolism. Neurons do not carry clocks that tick in seconds. Instead, the brain tracks change. It notices sequences, rhythms, and patterns. When many changes occur, time feels full. When few changes occur, time feels compressed. This is why a busy day can feel long, while a quiet afternoon seems to pass quickly. This biological time is flexible. It can speed up under stress and slow down during rest. It stretches during moments of danger and shrinks during familiar routines. None of this reflects a change in space-time itself. It reflects how the nervous system processes information. This distinction matters because it highlights how different physical time is from experienced time. Space-time treats time as a coordinate that can dilate due to motion or gravity. Biology treats time as an internal narrative built from events. Because we live inside biological time, it strongly influences intuition. We expect time to flow smoothly and uniformly because our brains usually construct it that way. When physics tells us time can behave differently, the idea feels foreign. Understanding this mismatch helps explain why space-time concepts feel so unintuitive. We're trying to map a deeply human experience onto a physical structure that operates by very different rules. This does not mean biological time is inaccurate. It is simply optimized for a different purpose. It helps organisms survive, not describe the universe precisely. Recognizing the difference between physical time and experienced time can soften confusion. It reminds us that difficulty in understanding space-time is not just a scientific problem, but a cognitive one. As we continue, we will widen the lens again and look at how space-time behaves across vastly different scales, from the smallest structures to the largest cosmic patterns. Space-time behaves differently depending on the scale at which we observe it. At human scales, its effects are subtle and easily ignored. At cosmic and microscopic scales, those same effects become dominant, shaping the structure and behavior of the universe in profound ways. On the larger scales, space-time guides the motion of galaxies and the expansion of the universe itself. Galaxies are not simply drifting through empty space. They're carried along by the expansion of space-time, moving apart as the overall geometry evolves. This large-scale behavior is smooth and predictable, governed by relatively simple equations. At smaller cosmic scales, such as within galaxies or star systems, space-time curvature becomes more localized. Gravity shapes orbits, bends light, and influences how time passes near massive objects. Even here, space-time remains well-behaved and calculable, as long as gravity is not extreme. At the smallest scales, however, the picture changes. Quantum effects dominate. Space-time no longer appears smooth and continuous in our descriptions. Fluctuations become significant. The assumptions that work so well at large scales begin to fail. This dependence on scale is not unusual in physics. Many systems behave differently when viewed closely than when viewed from afar. What is unusual is that space-time itself changes character across scales. It is not governed by a single, unified description that works everywhere. This raises an important point. When we say we do not fully understand space-time, we often mean that we do not understand how these different behaviors connect. How does smooth cosmic space-time emerge from whatever exists at the smallest scales? How do local quantum effects give rise to global geometric order? These questions remain open. They sit at the intersection of cosmology and quantum theory. They remind us that space-time is not a single object with fixed properties, but a structure whose behavior depends on context. As we approach the final sections, we will look for patterns that repeat across nature and consider how space-time fits into those broader patterns of organization and emergence. When scientists look across different areas of nature, they often find repeating patterns. Systems made of many interacting parts tend to show similar behaviors, even when the parts themselves are very different. Space-time may be part of this broader pattern. In fluids, for example, individual molecules move chaotically. Yet at large scales, smooth flows emerge. Temperature, pressure, and viscosity describe the collective behavior, not the motion of single particles. These large-scale properties are real and measurable, even though they do not exist at the microscopic level. Space-time shows signs of behaving in a similar way. At large scales, it is smooth, geometric, and predictable. At small scales, theoretical hints suggest complexity, fluctuation, and possibly discreteness. The smooth structure we observe may be an average, not a fundamental feature. This idea connects space-time to other emergent systems. Patterns appear not because the underlying components are simple, but because many interactions organize into stable forms. The rules that govern the collective behavior can be very different from the rules governing individual components. Seeing space-time as part of this pattern helps explain why it resists simple explanation. Emergent systems are often easy to use but hard to reduce. We can describe their large-scale behavior accurately while remaining uncertain about their underlying structure. This perspective does not diminish space-time's importance. Instead, it places it alongside other powerful emergent concepts in science. It may be fundamental to our experience, even if it is not fundamental in the deepest sense. As we move closer to the end of our exploration, we will bring space-time back to a more personal scale, considering how everyday life unfolds quietly within this complex structure. For all its complexity, space-time is also the setting of ordinary life. Every small action, standing up, sitting down, taking a breath, unfolds within its structure. We do not usually notice it, because space-time is stable and gentle at human scales. When you walk across a room, space-time is there, quietly defining distances and durations. Gravity holds you to the floor. Time passes at nearly the same rate for everyone around you. Nothing feels unusual, and there is no reason to think about curvature or relativity. Yet even here, space-time is at work. Your body follows paths through space-time shaped by Earth's mass, your heartbeat, your thoughts, and your movements all trace world lines, paths that combine where you are and when you are there. These ideas sound abstract, but they describe something deeply familiar. Aging itself is a space-time process. It is the accumulation of time along a particular path. Two people who follow different paths, different motions, different gravitational environments, will accumulate time differently, even if the differences are usually too small to notice. This perspective can feel distant, but it also grounds space-time in lived experience. Space-time is not only about black holes and galaxies, it is about waiting, resting, moving, and changing. It is the quiet structure that allows events to unfold in an orderly way. Recognizing this can soften the mystery. Space-time does not need to feel dramatic or overwhelming. Most of the time, it behaves calmly and reliably, giving life a steady rhythm. At the same time, knowing that this calm behavior emerges from deeper, unresolved physics adds a gentle sense of depth. Ordinary moments are connected to a structure that reaches far beyond everyday awareness. As we approach the closing sections, we will return to the central question and reflect on why, after all this exploration, space-time still remains partly unknown. After moving through all these layers, classical space and time, relativity, quantum conflicts, black holes, emergence, and everyday experience, we return to the original question. Why do we still not understand space-time? The answer is not that space-time is poorly defined. In many ways, it is defined with extraordinary precision. We know how it behaves across vast ranges of scale. We can calculate its effects, test them, and rely on them. In practical terms, space-time is one of the most successful ideas in science. What remains missing is a single, coherent picture that works everywhere and feels complete. Our best description of space-time depends on context. At large scales, it is smooth and geometric. At small scales, it becomes uncertain. When gravity is weak, the rules are clear. When gravity is strong, the rules strain and sometimes fail. This fragmentation is the heart of the issue. Understanding usually means unification, one framework that explains many situations at once. With space-time, we have multiple frameworks that work well separately, but do not yet fit together cleanly. There is also the question of depth. We do not know whether space-time is fundamental or emergent. We do not know whether it is continuous or discrete. We do not know whether it is a thing, a relationship, or a collective behavior of something deeper. These are not small details. They shape what kind of explanation is even possible. Importantly, this lack of understanding is not shrinking because the problem is trivial. It persists because the problem is deep. Each time we probe space-time more carefully, we find new layers of structure and new limits to our assumptions. In this sense, not understanding space-time is not a temporary failure waiting to be corrected by a single discovery. It may be a long process of gradual clarification, where questions shift as answers appear. Returning to the question calmly, we can say this. We do not yet understand space-time because it sits at the intersection of our most successful theories, our deepest experimental limits, and our most constrained intuitions. It is where knowledge is strongest and foundations are weakest at the same time. As we move into the final moments, we will step away from explanation and toward continuity, acknowledging that understanding unfolds slowly without sharp endings. Science does not move in sudden leaps as often as we imagine. Most of the time it advances quietly, through small adjustments, careful measurements, and patient refinement. Space-time fits naturally into this pattern of slow discovery. There was no single moment when space-time became understood, and there will likely be no single moment when it becomes fully understood. Instead, understanding grows in layers. Each generation clarifies something, resolves a tension, or finds a better question to ask. This slow pace is not a limitation of intelligence or technology alone. It reflects the nature of the subject. Spacetime is not just another object within the universe. It is the framework that holds all objects, all events, and all measurements. Changing our understanding of it reshapes everything else at the same time. Because of this, progress must be careful. New ideas are tested not only against experiments, but against the entire structure of existing knowledge. This naturally slows things down. Stability matters as much as novelty. There is also continuity across generations. Physicists today build on insights from decades and centuries ago. Questions about space and time that once seemed settled are revisited with new tools and perspectives. What remains unclear today may become clearer tomorrow, not through a breakthrough, but through accumulation. This continuity can be comforting. It means that not understanding spacetime fully is not a gap waiting to be closed urgently. It is part of an ongoing process that unfolds at human pace, guided by curiosity rather than pressure. For listeners wrestling with these ideas, this matters. There is no need to resolve the question tonight. Spacetime does not demand immediate clarity. It allows for gradual familiarity, even without final answers. As we prepare to close, we can let the idea of spacetime gently open, something that works, supports life, and invites exploration without insisting on completion. We began by noticing that spacetime is both familiar and elusive. It shapes every moment of life, yet resists full explanation. After moving through its ideas, limits, and open questions, we arrive not at a final answer, but at a quiet stopping point. In science, not all understanding comes from closure. Some understanding comes from learning how to live with uncertainty without tension. Spacetime invites this kind of understanding. It supports everything we do, even while remaining partly unexplained. You do not need to hold its equations in mind. You do not need to resolve its paradoxes. For now, it is enough to recognize that spacetime behaves reliably, gently, and consistently at the scale of rest and sleep. The deeper questions can remain where they are. As your breathing slows and your attention softens, spacetime continues its calm work. Time passes, distances hold, events unfold quietly, without asking to be understood all at once. Curiosity can rest too. Questions do not disappear when we stop thinking about them. They simply wait, carried forward by time itself. Everything flows. Sleep in that motion,